afterwards. So it'll be due, I guess, a week and 2 days officially. But if you have it done early, feel free to hand it in and just laugh at all those people who are still working on it.
Yep, I did it.
Now, so there's two big thrusts for chapters 4 and 5. So, any questions before I talk about the two big thrusts for chapters 4 and 5? So the two big thrusts from chapters 4 and 5, one is to be able to identify forces involved in the problem. The second one is to actually do the analysis. So let's actually go through an analysis problem. Again, I'm skipping over a lot of the preliminary stuff because there are videos which cover this. But I do feel like I've got to do at least one inclined plane. Now, traditionally, I shouldn't say traditionally, I've never seen any example against this, and that would be very bizarre if it did. Mu sub s is bigger than mu sub k. Like I said, I've never seen an example where mu sub s was smaller than mu sub k, but I guess correctly, I have seen various student labs, friction labs, where they have come upon this potentially Nobel Prize winning work. And also the question has come up, if you go to a list of coefficients, I think you'll notice that there are no coefficients bigger than 1. And so the question has come up of, is it possible to, and it is actually possible for the coefficient to be bigger than 1, it's just that it's rare. All right, so this was the facades. Again, there are videos where I go through each step. And I've done the inclined plane problem, but we will do it also. So the first thing you do, the F here is for the force diagram. We're going to do exactly what we just did. If you see the hash marks like that, that's indicating that basically you have an object that's fixed. That the wedge here is fixed to the ground. I could also represent the wedge not moving as I could have done it like this, just to make it clear that it's part of the ground. If the wedge does move, then we're introducing a far more complex problem. A mildly more complex force diagram, but the actual analysis becomes far more complex. And so the first thing to do is the force diagram. Now what I really care about is what's happening to the box here, but I am going to include the wedge also, just for completeness. And I got F-tom. What are the forces acting on the box and or the ground?
Gravitational force of the box is when you press this ground.
Which way on the box?
Downward.
Okay.
And then outward from the ground.
All right, so weight. Now technically this force right here coming up on the ground is acting from the center of the earth, but so anywhere in what are represented as the ground works. I have only one small object and one huge object, so I have only one hair there, so I'm done. I don't need a subscript since I don't have any other small objects. Acting which way, on what?
The incline is going this direction up on the box.
So the force is going that way,
Yeah,
on the box?
yeah. And then the box is acting in the opposite direction onto the ramp.
And one of the biggest mistakes I see here is people always, is going back to something Thomas said earlier, putting the normal force opposite the direction of weight. There are a whole lot of problems where that works, but not here. It is still perpendicular to the surfaces of contact. Again, I have only two objects touching, so normal force done.
There's no other force.
All right. Done.
No tension.
Friction would be pointing that way on the box and that way on the ramp, because it's opposite.
All right, so that way on the box, that way on the ground, or ramp.
Yes.
Anyone want to counter that?
With the boxes going down,
Right?
so the friction would be the other way.
So friction is helping it move down the ramp?
So the box is going down, right?
The box wants to slide down. Whether it's actually moving or not, I don't know yet.
But the friction's going, go ahead, Kate, go ahead.
Yep, friction opposes it.
Because this, yeah.
So friction is acting this way on the box, because the box wants to slide that way. Friction says, not in my house. Again, all I really care about are the forces acting on the box. At some point, you do enough physics, you start to realize, oh, I really don't need to do that part of it. But it did part of it, again, just as practice. But this is the part I care about. So that's the F in facades, the facades method. Questions up to there before we do A, the first A? All right, for what does the first A stand? What does it represent?
Acceleration direction.
Yep. What is the direction of the, if this box slides, which way is it going to accelerate? I heard down, but the gestures I'm getting are at an angle.
Yeah.
Yeah, it's not gonna drop down. Now, there's a certain amount of, I could have misheard, that's possible, but I've heard enough people say down in the past that I projected. Down is defined by the direction of the gravitational pull. And so if you say down there, that means straight down. So down the ramp. So my acceleration is going to be down the ramp. And so let's go, it's not part of the force diagram, despite what some students have tried to pull in the past. Acceleration, sort of drawn it separate, is in that direction. So that's that A right there. And now the CA. Any questions about the direction of acceleration before someone reveals what CA stands for? All right, somebody reveal what CA stands for what it stands. Yes. Strongly recommended. And I think I've actually done this video of solving this the hard way, box on ramp the hard way, where I stick with the classic brainwashing coordinate axes like this. This is not the simplest way, it's far more complex. Instead, strongly recommended that one of my axes is in the direction of acceleration. That's the whole point of figuring this out first. Now, there are some situations where you just don't know, but there are some of them where it's very clear that box, I think all of us can imagine, If I have a ramp and I put a box on it, it would slide down the ramp as opposed to suddenly just lifting off of it or going in some strange direction. Which would be a cool effect, but it would really destroy this problem. So my coordinate system, I'm gonna have one in the direction of the acceleration, and I'm gonna call that my I hat direction. And then J hat is perpendicular to it. Please stick with perpendicular unit vectors. So J hat could either be away from the ramp or towards the ramp. And it actually does not matter. Out of brainwashing and habit, I'm just gonna put J hat that way. But if you prefer J hat to be in the other direction, more power to you, no problem. Now the fact that I drew them different lengths has no meaning other than the fact that I can't draw them. All right, now I've set up my coordinate system. The D is for not direction.
Decomposition?
That's it, right there. We're basically going to take any vector that we need to and break it up into its components, into perpendicular components. So I look at my three forces. I want to pick any force that's not in the positive or negative I hat direction or not in the positive or negative J hat direction. Are any of these forces not in the along my axes? Are there any forces? So again, I drew my coordinate system so that I'm dealing with parallel to the ramp and perpendicular to the ramp. Are there any forces not parallel or perpendicular to the ramp? Yes. Normal force is in the positive J hat direction, friction's in the negative I hat direction, weight is in a combination. Weight is what we need to break up. I want to break weight up, I have weight acting straight down. I want to break it up into a part that is in the direction of I hat and opposite direction of J hat. I want to break it up into perpendicular components so that I can relate it simply into I hat and J hat. Now, this is a right triangle here. Think back to our original problem. This is a right triangle here. One of these two angles is 27 degrees and the other one is the complement to that. 63 degrees. Now, I have not drawn it particularly well. But one approach to figuring this out is to actually try to draw it properly. 27-degree angle, so 45. So that's roughly 45. 27-degree angle would be much smaller than that. So my ramp is actually more like this. I have weight acting down. And I want to break it up into perpendicular components here. One of my angles is 27 degrees. The other one is, I think it's 63 degrees. I'm looking at this right here. Which one of these is the smaller angle? That's the 27-degree angle there. So one approach is just to try to draw it somewhat accurately and pull it from there. The other way doesn't depend upon drawing skills. I've got weight, I have weight acting down. I'm breaking it up into components, so part of it is along the direction of the ramp, the other one is perpendicular to that. This is some angle theta, 27 degrees in our example here. If that's theta, what is this angle right here? Is it phi?
Yeah, isn't that what it's called?
You could, but in terms of theta, what is this? I have a right triangle here. If this is 30 degrees, what would that angle be?
I'll do 30.
I've heard several different numbers being tossed out here. This would be 30 degrees? 60 degrees. Then we want to make an argument for 30 degrees. It would be all right, suppose this was 20 degrees, what would that be?
70.
What's the pattern?
90 minus theta.
Yeah, so this is 90 minus theta. 90 degrees minus theta. If you're a radian fan, that's pi over 2 minus theta. Or what I'm just going to label this as theta prime, just to indicate it's the complement of theta. I also have a right angle here because weight is acting straight down. So what is this angle right here?
Theta?
45 degrees.
It would not be 45 unless theta is 45. These two angles are the same. Just like I had right there. So my hypotenuse is what I'm breaking up. My hypotenuse is the weight. That's my hypotenuse along there. This side along here, is that opposite theta or adjacent to theta?
Opposite
It is. Which trig function is associated with opposite?
sign.
So this is weight times the sine of theta. And this one's the other one, so this would be weight times the cosine of theta. What I'm claiming here is that I can take my force diagram. I had normal force going this way. I have friction going this way. Down the ramp, I've got W sine theta. And into the ramp, I have W, or towards the ramp, I have W cosine of theta. What I'm claiming is that I can take my weight vector here and I can break it up into these two pieces. If I add these two together, I should get this. And that's the decomposition phase. Questions before we get to E?
For the, I guess, test, do we have to show all of like every single one of these steps?
Typically, and this is test 1B, not 1A. Typically, there's going to be some problem where I just say, what are the, and recently I've been on the pattern of, I give you a problem with forces I give you the force diagram and say, what is the equation of motion?
I didn't know if I like just threw down, W sine theta minus, all of that, or if I had to show my work with.
Now, if you're given the angle next to the horizontal here, it's going to be W sine theta down the ramp, so you don't need to show me how you got W sine theta and W cosine theta.
Okay.
If you have a test moment and suddenly you're going, wait, I know it's one of them or the other, it might be helpful to show it, but
Right. I was just asking if it was required.
yeah, as with any work on a test, 99% of the time it's helpful for me to see your thought process, but not required.
So, when you're doing a ramp problem, you're always gonna use the hypotenuse as the force of gravity, and then sine theta would usually be the ramp, or not?
Whatever you're decomposing, whatever you're breaking up, is always the hypotenuse.
Okay.
So in this case, we happen to be breaking weight up, so weight, that
Yeah, that makes
decomposes.
sense.
When I solved this the hard way in one of the videos, using my axis like this, that's the hypotenuse I break up, and that's the hypotenuse I break up. Other questions?
So
Yeah, Dylan?
you were saying you use two different, I'll just watch the video.
there's a version of it where I solve it basically what we're doing right here, and then occasionally I have students who want to make these the coordinate system instead of tilting it, just because in math class, it's always horizontal and vertical. And what I hope to get across in that video is, it's a lot harder to do it that way. And so there, yeah, so if you watch it, hopefully that will become clearer.
You gave us, friction, are we, in this particular problem, are we solving for anything, like acceleration, or, because
You
the
know-
box doesn't have a mass either.
It does have a mass. Would you like me to give it a mass?
Yes.
Okay. Any particular mass?
An easy one.
I use 1,
12.
12? Thank you for speaking loudly there. 12 kilograms. Typically, yes, I didn't actually state the problem. We're just sort of exploring, but typically it'd be, what's the acceleration of the box?
Would that answer be what we're figuring out for W? Or,
Sorry, ask again?
never mind. That was.
Okay. Get rid of this stuff, because I need room. Still waiting for that portable board to show up. All right, so now E. E stands for,
Equations of motion.
yes. The equations of motion are based upon F equals ma. There'll be two equations of motion here. One of the equations will be in the I hat direction, the other one will be in the J hat direction. For the I hat equation, please don't write I hat equals, this is just differentiating the two equations here. So my I hat equation, so I look at the forces in the I hat direction. I've got basically, I have friction, I have W sine theta. Which one of those forces is in the positive I hat direction? Yep. So write down W sine